Hello, I'm Mr. McBrien. This is TEJ3M, Basic Circuits. So today we're just going to introduce some definitions around electricity and talk about Ohm's Law, getting ready for some in-depth study of building circuits. So I'd invite you to think about your understanding of electricity and what it really is. We can start with thinking about the idea of static electricity. I imagine you came up with something to do with the idea of the flow of charge, or possibly something to do with power. And really, electricity is something a bit different than that. The charge aspect is certainly true. An excess of charge on an object, whether it's positive or negative, is a definition of static electricity. And, of course, static meaning not moving, we can infer that the electricity in this case doesn't move. And static electricity is useful for gaining an understanding of what charge is, but it's not extremely useful in terms of computer engineering. We measure an excess of charge in units called coulombs, and those are equivalent, 1 coulomb is equivalent to the charge of about 6.2 times 10 to the 18 protons. So is a charge, it's an observable charge on something. And we won't talk about coulombs too much because we won't talk about static electricity very much. Instead, what we want to talk about is the movement of electricity, so current. And no great shock, current is the speed at which electricity moves. We measure it in amperes, and amperes just mean coulombs per second. So an amount of charge divided by time. So if the amount of charge moving goes up, the amperage goes up. If the time goes down, the amperage goes up. We usually label current on a schematic as an arrow from positive to negative. So positive current is positive charge moving in a given direction. Now, why does electricity move? Well, the answer is because there's a potential or a potential difference applied across a conductive material. And that's usually provided by either a power supply or a battery. And those things provide this push, this potential difference to make electrons move. The units of potential, volts, and we won't get into the derivation of volts, but that's okay. We don't really need to know that. We just need to know that the greater the voltage, the greater the push on the electrons, the more the tendency for electrons to move. Symbol for a battery in a schematic is a series of lines representing cells. Now, in this case, our picture is redundant. We showed the positive and the negative terminals of the battery, but these are also shown by the direction of the wide versus narrow bars on our cells. So the fact that the wide bars are at the top means that the top is the positive terminal. And this is very important for predicting the flow of electricity. Okay, so any given circuit needs what we call a load. We have to resist the flow of electricity, otherwise we have a short circuit. Electricity flies too fast, and we can see things like fires. Now, the resistance to the flow of electrons, it's based on work done by some device. It might be a motor moving an elevator. It might be a light bulb providing light, or it could be simply some kind of material that doesn't conduct all that well, providing heat. At any rate, if work is done, then we see a resistance. We measure that resistance in ohms with the symbol of the Greek omega. And in schematics, we usually show resistance as a representation of a coiled wire, shown by a series of diagonal lines. All right, now we've defined current, we've defined potential, and we've defined resistance. We can relate these things together very simply. So, our current goes up when voltage goes up. Our current goes down when resistance goes up. And so our relationship can be roughly predicted by that relationship, I equals V over R. I representing current. Okay, and this is all a review, of course, from science class, but it's so important to this unit that it's useful that we go through this in a little bit of detail. So we can apply Ohm's law to take a circuit like this one with a 200 ohm bulb attached to a 9-volt battery, and we can calculate the current pretty simply. Remember that I equals V over R. And so it's 9 volts divided by 200 ohms, or 0.045 amperes. And we can rearrange the equation to do things like determine the voltage required to get 0.02 amps with a 1000 ohm resistance. So in this case, we rearrange the equation, V equals IR, and we see that we need 0.02 times 1000, or 20 volts, to get 0.02 amps. And of course, we can flip that around for the other calculation that's implied by that equation. So in this case, if a 12-volt battery gives us 0.1 amps of current, we can determine the resistance by, again, rearranging our equation, R equals V over I this time. And when we divide 12 volts by 0.1 amps, we get 120 ohms resistance. So if a 12-volt battery gives us 0.1 amps of current, the resistance of our circuit must be 120 ohms. All right, so those are some basic calculations and review from science class. Remember that potential is the force that pushes electrons through a circuit, and it's measured in volts. Current is the speed of movement of charge around the circuit, measured in amperes, or coulombs per second. And the resistance of electrons to moving is, fittingly, the resistance measured in ohms. And we can relate very simply the product of current and resistance is the potential, V equals IR, or the current is equal to the voltage divided by the resistance, if we want to rearrange that. Okay, so for your homework for today, please complete the activity sheet and the Ohm's Law worksheet in preparation for tomorrow. Thanks very much, and have a great day.